Hello everyone, welcome to week 5 of the course Introduction to Semiconductor Devices by Professor Naresh Kumar Imani from IIT Hyderabad. The course ID is NOC 25E92. I am Mayank Goyal. I am a research scholar at the Department of Electrical Engineering, IIT Bombay. This course is being taught by Professor Naresh Kumar Imani, who is an associate professor in the Department of Electrical Engineering at IIT Hyderabad. The course plan for the week 5 is PN junction under applied bias, minority carrier injection, and special variation in depletion in quasi-neutral regions, band bending under applied bias, and ideal diode equation. So this live session is happening every Sunday 6 p.m. to 8 p.m. at this Google Meet link. So first we will do a recap of the this week's lectures doc by the document provided by Professor Imani. So this week we will study what happens when we apply bias across the PN junction. So there are two types of biases that you can apply. One is forward bias, where the higher potential side is applied to the P type and the lower potential side is applied to the N type. And another is reverse bias, where the higher potential side of the battery is applied to N type semiconductor and the lower lower potential side of the battery is applied to the p-type semiconductor. So what happens in forward bias is that the majority carriers diffuse into the depletion region, and due to that the depletion region reduces, the width of the depletion region reduces, and hence there is a net flow of net flow of current. Whereas in reverse bias, the majority carriers move out of the PN junction and hence increase the depletion region, and they are unable to conduct, hence the conduction is very low. So what happens in forward bias? So in at equilibrium condition, this is how the band diagram of a PN junction looks. So this is the P side where you have excess holes for conduction, and this is the N side where you have excess electrons for conduction. When you so when you apply for positive potential to the P side, what happens is that the Fermi level here reduces with respect to the Fermi level here, and brings it, hence it brings the whole band down. So the band starts looking like this. You can see the quasi Fermi level in the P side EFP is at a lower potential than the quasi Fermi level, and the N side EFN, and the gap between the conduction band and P side and N side has also reduced. So it makes it easier for movement of movement of charge movement of charge carriers from one side to another side. Now this is the recipe for drawing this type of band diagrams. So you first consider a zero potential line, imaginary line for zero potential, and then you draw EFP below that for a particular VA. So if VA is positive, then EFP will be negative, will go down from the zero line, and if VA is negative, then EFP will go above the zero line. And then you draw EC and EV accordingly to this EFP. Draw EC and EV here. So EFN will stay at the zero line. Only EFP will move according to the VA, because we are considering that the applied potential at the N side is zero, and all the VA is applied at the P side. So hence EFN is we keep at zero. EFP moves according to VA. If VA is greater than zero, EFP will go down. If VA is less than zero, EFP will go up. Then you draw your EC and EV according to EFP and EFN, and then you join them while keeping EG constant. So when you do that, so this is in the neutral condition where there is no applied bias. So when you apply a forward bias, your EFP goes down. So EFP goes down, EFN stays the same, and when EFP goes down, your EC and EV also go down. So hence the so earlier your built-in potential was Q VBI. Now your built-in potential has reduced by VA. So now your new built-in potential is now Q VBI minus VA. So which allows electrons to go from this direction. Electrons to go from N side to P side, and holes to go from P side to N side. And this results in a net diffusion current. So one important point, that the minority carrier density is small, so drift current can be neglected in forward bias, because the diffusion currents in this case are very high compared to the drift currents. So you can ignore the drift currents. Similarly, when you apply reverse bias, so your EFP will now move up. So when you move your EFP up, now what happens is your EC and EV also move up, and now your built-in potential increases. So it's now in Q VBI plus VA. It's minus VA because VA itself is now negative, but if we consider VA positive, then it's VBI plus VA. So the magnitude of this increases. So now your potential barrier across the junction has increased. So it causes it. So there is no diffusion current now, but drift current is always present. So now, since the diffusion current is not there, now we only consider drift current. So In forward bias case, since the diffusion current is so very high, we neglected the drift current, but in reverse bias, there is no diffusion current, so the drift current becomes significant. So you can see here how the band diagram says for reverse bias and forward bias. So this is the neutral condition when there is no applied bias across the junction. When you apply a reverse bias, what happens is the the majority carriers move out of the junction because of drift current, and this increases this increases the net depletion width and also increases the potential barrier as we have earlier studied. So this is how your reverse band diagram will look like for reverse bias, where the potential barrier is increased by your applied potential. Similarly, when you applied a forward bias, your carriers will move into the depletion region and reduce the depletion region, and your barrier is also decreased by the applied potential. So the so your band diagram will look like this. So for reverse bias, your potential barrier increases. There is negligible diffusion current, so drift current is important, and also depletion width also increases. when you give forward bias, then diffusion barrier decreases, diffusion current is dominant, so you ignore the drift current, and you also your depletion width is reducing. Now we come into the statistics part of it. So excess minority carrier injection for forward bias case. So what happens is the applied bias causes injection of minority carriers across the junction into the junction. So this is how you draw ca- your carrier dynamics with respect to length. So in the depletion region, the carriers are depleted, so don't draw any carriers in the depletion region. And outside the depletion region, ideally you have n in the p side you have n minority carriers. In the n side you have p minority carriers, which are ideally given by ni square by na for p side and ni square by nd for n side. Now there is injection of minority carriers from the from the junction to the semiconductor. So that we consider this point np of minus xp. Similarly, here you have npn of xn, and now we have to see how they will look like. So the formula to calculate is the same as earlier, where n equals to ni exponential efn minus ei by kt, and p equals to ni exponential ei by minus efp by kt. So when you multiply this, you get np equals to ni square exponential EFN minus EFP by KT. And we know that in our we know that from earlier our EFP minus EFN is our applied bias. So EFP minus EFN becomes QVA. So your NP equals to Ni square exponential QVA by KT. So this will be valid all across the PN junction. So this then you can put here NP of minus XP, PN of minus XP, PP of minus XP equals to Ni square by Na exponential Q QVA by KT. So P so the P of P of minus XP is Na that we know from here. This is that are majority carriers, so there will be Na, and Na is also here. So we can put it here and it cancels out. So this becomes NP of minus XP equals to N of P naught, which is your base, which is your base minority carrier density exponential QVA by KT. Similarly, for P side, it will be Pn at Xn equals to P of N naught exponential QVA by KT. So this so you can see here. So, so the excess minority carriers at the edges of the junction are NP minus XP equals to NP not exponential EVA by KT, and PN at Xn equals to PN not exponential EVA by KT. So we have made some assumptions here. There are no generation and recombination in the depletion region, and the values for PN and NP are not changing across depletion region. So what if VA is 0? Then PN equals to PN naught, NP equals to NP naught, which means there are no excess minority carriers, which is the equilibrium condition. Now we need to see how does minority carrier density change with X. So which is the simple case of which is the simple case of steady state diffusion, which we had studied in the last two classes. So we will take we will take a cutout of the n-type junction. So you have a you have a excess carriers at the so if we take zero, we consider this, assume this to be zero of our n side. So at zero we have a excess carrier density given by this Pn not exponential EVA by KT. So they will then diffuse into the n side, n type, and the dynamics for that we already know. So for study, so it will be Pn not exponential QVA by KT x into exponential minus x by LP x. So because it's not zero, it's xn. So it becomes minus xn by LP. Similarly, here it will be np naught exponential qv by kt into exponential x by ln. Again, for x you will have to change to xp, so it will become x plus x minus of minus xp, so x plus xp by ln. So there will be an exponential reduction of excess carriers as they go into the semiconductor away from the junction. and the depletion is given by the diffusion length values LP and LN. So if we want to plot this on our band diagram, our band diagram will look like this. So for E, so for EFN, so if we are plotting and we are plotting N type carriers. So here we know our E, so here we know our N type carriers are equal to our N type carriers are are equal to our majority carriers, so they are constant. And we have just made the assumption that they don't change in the depletion region, so here also they're constant. And in the minor in the p type region, the electrons become minority carriers, so they are going depleting exponentially. When you plot this on potential line, when you plot this in terms of potential, it becomes a straight line. So it will go a straight line like this. So as it as as our minority carriers approach their equilibrium value, EFN starts becoming equal to EFP, and it at certain point it merges into EFP. Similarly, if you take holes, so EFP goes like this straight line because it's majority carrier in the type. It does not change in the depletion region due to our assumption. And for when it goes to N type, it becomes minority carrier and starts diffusing. So it starts merging into EFN at some point. EFP and EFN merge. So very far from the junction, we have only one Fermi level. Here it's EFP, here it's EFN, but near the junction we have two Fermi levels. So that is why these are called quasi Fermi levels. So now question: calculate the minority carrier concentrations at the edge of the space charge regions in a forward junction bias PN junction. Consider a silicon PN junction at T equals to 300 K. Assume doping concentration in the N region ND equals to 10 per 16. Doping concentration P region Na equals to 6 into 10 per 15. And assume forward bias of 0.6 volts. So if we have to calculate a carrier concentration at this point, then this will be P N naught exponential Q VA by KT. So we can calculate P N naught by doing Ni square by Nd. So which is 10 per 20 by 10 per 16, which gives 10 per 4. VA is given as 0.6, and Q by KT by Q for 300K is known as 26 millivolts. So we solve this, we will get around a bit. If we solve this, we will get something 10 per 14, 10 per 15. Similarly, for this side, if you calculate NP naught, which is Na square by Na, that comes out to be around 2 into 10 per 4. You so that you put in the same equation, so it will come out around similarly this value, double this value, so around 2 into 10 per 15. If this is 10 per 15, so that is how you can calculate. So you can see at this your ND is 10 per 16 and your NP itself is 10 per 15. So they are your minority carriers at this point are 10 per 15, where it's your majority carriers are 10 per 16. So the excess minority carriers are very significant compared to equilibrium condition. So we had just studied for reverse bias there is no diffusion, only the small only the small amount of drift current is present, whereas in forward bias there is huge amount significant diffusion current. And we have also calculated the amount of excess carriers generated at the edge of the junction for forward bias, and the diffusion equation will be given as Pn of x equals to Pn of xn at this point, exponential minus xn by Lp. And for p set, Np of x equals to Np of minus xp, which is this point, exponential x plus xp by ln. So the so this excess carriers will result in diffusion current, which is, so there will be a diffusion current on the p side of electrons, there will be diffusion current of n side of holes. So so the the electron diffusion current is once on in a different direction and hole diffusion current is in a different direction. So the total current will be the sum of both, since sum of the electron diffusion current plus sum of the hole diffusion current. So electron diffusion current is given as q na d delta n by dx. Hole diffusion current is given by minus q dp d delta p by dx. So this minus sign is coming because hole current is in the opposite direction of electron current. But when you solve d delta p by dx, that will also result in a negative sign. So ultimately it becomes positive, and the net current is sum of both. So as you can see, your dn by dx will increase in this direction, or dp by dx will decrease for positive x direction. So hence the double negative will make it positive. So what will the value for delta Pn of x? That is given when you so that is given as the excess at the x set equals to x minus x of n. So that is Pn naught exponential q Va by kt. So into exponential minus x by xn by Lp, and you subtract it from, and from this you will subtract your id you will subtract your base value, which will be n naught. So hence there's a minus one value here, because you have to calculate only the excess value. Only the excess value you want, not so this is the value of p of n at the at x equals to xn, but the value you want is the excess value. So you subtract p of n naught from this, and this minus one is coming here, and this is exponential minus x minus xn by Lp, you know, from the diffusion dynamics. So when you take derivative of it, you get p of n naught exponential q Va by kt minus 1 exponential minus x minus xn by Lp into minus 1 by Lp. So Jp diffusion is minus q dp d delta p by dx. You multiply, you get q dp by Lp Pn naught exponential q Va by kt minus 1. And similarly, you can calculate for n type. So your net current, your total diffusion current will then be q dp by Lp Pn naught plus q dn by ln np naught exponential q Va by kt minus 1. and this, if you calculate, this is the drift current, drift currents. So for reverse bias, this will be the current you will get. If you calculate for reverse drift currents for reverse bias, you will get these values. So hence this is called reverse saturation current, because this is the value you will get in reverse bias. This is the current value you will get for reverse bias. Next is, so we have calculated current in the PN junction. So for in forward bias condition, the current will be J equals to Js exponential Q VA by KT minus 1, where Js is Q dn by dn and dn by ln np naught plus Q dp by lp pn naught. So if you plot this, so if you see, if I make it, if I make my VA negative here, so this value exponential QVA by KT becomes very small. So, and due to minus 1, we can neglect this value. So for reverse bias, the value becomes J equals to minus Js. Hence for reverse bias, the my current value is given as minus Js, and forward bias it's exponentially increasing. So if you plot this if you plot this, you will get a line like this, and so the point at which it becomes a very high value, we we take we extrapolate a straight line backwards, and this is to get a val to get a value. This is called threshold voltage, or also known as knee voltage. So our knee voltage is the value at which our PN junction starts conducting. So below knee voltage or threshold voltage, the value is the current value is negligible. After that, it becomes significant. So we have, so at high VA value, this becomes very large. So minus 1 can be neglected. At negative VA value, this becomes very small, and this can be neglected. So we can assume if VA is greater than 0, J is approximately Js exponential Q VA by KT. If VA less than 0, then J is approximately minus Js, where Js is Q dA by N LA and Pn naught, which is Na square by Na, plus Q dP by Lp Np naught, which is Na square by Nd. So you can see this is exhibiting a strong dependence on Eg and T, and the typical values, these are typical values for Ni. So if you have one-sided junction where N, let's say for Na greater than Nd, where one side is heavily doped compared to other side. So for that, if Na is greater than Nd, then this value will be very small compared to this value due to Na and Nd in denominator. So you can say then Js becomes just this value. So then J is now Q dP by Lp Ni square by Nd exponential Q Va by Kt minus 1. So we have already studied this. So this is diffusion and this is drift current. So what happens in reverse bias? So at reverse bias, what happens is that the all the we assume that the minority carriers at the end of the junction are zero now. In reverse forward bias, they were excess. In reverse bias, they are zero. So there will be diffusion of current towards the junction. In forward bias condition, the minority carrier current was moving away from the junction. Here the current will be in towards the junction, hence the current is opposite to the forward bias condition. So what happens here in reverse bias is the potential across the junction becomes equal to the applied potential. So hence this becomes 1. So Pn of xn becomes equal to 0. So this is 1. 1 minus 1 becomes 0. Here also it becomes 1 minus 1 0. So the values, so your minority carriers at uh, edges of the junction are 0, and hence as they go, so there is drift drift of value drift of minority carriers towards the junction to for maintaining equilibrium. So your drift current is given as q and mu and electric field. So as Va increases in reverse bias, that is the magnitude is increasing, your depletion width also increases, and your electric field also increases. But but once your but this is only till the this value only increases till the point your minority carriers get depleted at the junction, at the edges of the junction, and then they become saturated. Hence there's a hence it first increases with your Va, and after that it becomes saturated. So the current is limited by availability of minority carriers. So once they are fully depleted, your current saturates, and hence it's called a reverse saturation current, which is equal to Js. Determine the ideal reverse saturation current density in a silicon p-n junction at 300K, considering the following parameters: Na equals to Nd equals to 10 power 16, Ni equals to 1.5 into 10 power 10, Nd is 25 centimeters square per second, sorry, dp is 25 centimeters square per second, dn is 25 centimeters square per second, dp is 10 centimeters square per second, tau p naught equals to tau n naught equals to 5 into 10 to the minus 7 seconds, epsilon r equals to 11.7. So our ideal reverse saturation current density is given as Js equals to q dp by lp pn naught plus q dn by ln np naught. So you put the values for lp equals to under root dp tau p, and ln equals to under root dn tau n. So dp and under root dp cancel, dn and under root dp cancel. So you get under root dp by tau p plus under root dn by tau n. This values you can calculate from Na Nd. So you will get Na square by 10 power 16, which is 2.25 into 10 power 4. So this is what you get. So now you get 25 by 5 into 10 power minus 7, and this is 10 10 divided by 5 into 10 per minus 7, which you solve with, if you solve this, it comes approximately, the final value you will get is 10 per minus 12 ampere per centimeter square, which is typical values you will get for reverse saturation current in picoamperes per centimeter square. So this falls right into in our in the typical values regime. So this we have studied how the current looks in forward, how the current will look in forward bias condition. So this is how the diffusion current for minority carriers looks, and this is how the diffusion current for majority minority carriers will look in this side. So this dashed line is the majority carrier current. So that is the excess carriers that will flow to recombine with the excess minority carriers. So the that is shown here, but ideally the so if you add up both values, your total current, your total value will remain same. So hence your J total remains same. Calculate the electric field in a neutral region of a silicon diode to produce a given majority carrier drift current density. Consider a silicon PN junction at T equals to 300K with the parameters given in example 8.2, with the applied forward bias VA equals to 0.65 volts. So the parameters we had in the previous question, we have to use the same parameters, and we have to calculate the electric field. So for 0.65 volts, if you, so JS we had calculated 10 per minus 12. If we calculate this, it comes around exponential 26. So if we multiply it, we will get around 1 ampere per centimeter square. Now this is equal to the drift current. This is same as the drift current we will get for majority. So the minority carrier diffusion current will be same as the majority carrier drift current to maintain the balance. So n we know 10 per 16, mu n we can calculate from the dn, from the given dn value in the previous question, which was 25. So it will come around 1350 centimeter square per volt second. So if you multiply, if solve this, your electric field comes out around 1 volt per centimeter. So this is very low value compared to the electric field that is across the depletion region, which is around 10 per 4 volt per centimeter. So next topic is capacitance of the PN junction. So we know due to depletion of carriers, this is this acts as a fixed charge insulator. So hence there's a capacitance associated with the depletion region. So capacitance is given as dq by dv, and q we know is given as q na xp. We had from for abrupt junction, q is given as q na into xp, which is q na by na plus q na nd upon na plus nd w, which is the for value for xp. So if you do dq by dv for this, you will get capacitance equals to epsilon si by w depletion. So capacitance given epsilon a by d for this, for a parallel plate. We can take assume it as a parallel plate capacitor where charge is stored at the junction edges. So the capacitance for a parallel plate capacitor is given as C equals to epsilon A by D. So we don't consider A because we are always talking in terms of per unit area. So our capacitance per unit area becomes epsilon by D, and D in this term, this is W depletion width, and depletion, hence your capacitance is epsilon Si by W depletion, and depletion width is given by 2 epsilon Si by Q Na plus Nd upon Na Nd Vbi minus Va per half. So this is our built-in potential, and for in bias condition, our built-in potential is given as Vbi minus Va. So in reverse bias, the minus Va will change to Vr because Va will be negative. So this will be higher in reverse bias and lower in forward bias. So when this goes in the denominator here, this everything is constant. So our C depletion becomes perpendicular to 1 by square root of Vbi plus Vr. So it is, so yeah, the capacitance is dependent on the voltage. So this is the full value. C depletion equals to ESI upon square root of 2 2 epsilon Si by Q Na plus Nd upon Na Nd Vbi minus Va. So we take Va equals to minus Vr for negative, for reverse bias. So the capacitance is proportional to 1 by square root of Vbi plus Vr. So what we do is we take the square of the capacitor and inverse it. So 1 by C depletion square becomes W square by epsilon Si. And if we open it, and if we assume Na is greater than Nd, that is one-sided junction, then this Na plus Nd upon Nd just becomes 1 by Nd. So this value then becomes 2 by epsilon Si Q Nd into Vbi plus Vr. So if we plot 1 by C square versus Vr, we will get a straight line, the slope of which is given by 2 by E epsilon Si Nd. And and if we extrapolate it, we can calculate our built-in potential. So, question, calculate the junction capacitance of a PN junction. Take the same junction as in the previous question, assuming VR equals to 5 volts. So, if you solve for this 2 epsilon Si by Q Na plus Nd upon Na Nd Vbi minus Va per half, where instead of V minus Va you take plus 5. So it will be Vbi plus 5 volts. You solve this, you will get around zero point 0.5 microns, and epsilon is given as 11.7 into epsilon naught. So if you solve this, you will get around 100 into 10 per minus 10 farad per centimeter square, which is 1 picofarad per centimeter square. So this is the junction capacitance for reverse bias, since there is no conduction in the reverse bias. Similarly, for forward bias, there is something called diffusion capacitance. So this equation that we had studied, J equals to Js exponential QVA by KT minus 1. This is called ideal diode equation. So we had made assumptions in for solving this. So we had made the assumptions that current remains current remains same in depletion region. So we had made assumptions that the carriers are constant in the depletion region, hence the current doesn't change in the depletion region. And we had also assumed low level injection, where the excess carriers generated are less than the majority carriers. So if we separate it in forward and reverse conditions, so forward you will get a straight line with a slope q by kt. So this is so you can see this is q by kt is at a given temperature is constant. So forward the slope will be constant always. If we plot log of this versus Va, and in reverse bias you will get a constant current which is given as which will be Js. Next we talk about junction breakdown in reverse bias. So if we go very high values in reverse bias, at a certain value the junction breaks down and the current becomes and the current shoots up suddenly. So there are two types of breakdown. One is Zener breakdown and one is avalanche breakdown. So what in Zener breakdown, what happens is that the the junctions are doped very high, hence the barrier is very high and it becomes very narrow, and due to excess doping there are lots of free states available. So what happens is that this when this becomes very narrow, the electrons start tunneling from p side to n side, and So from valence band of p side, it electrons start going to conduction band of p side, conduction band of n, valence band of p side to conduction band of n side. So hence this results, and we know there is the valence band, there are is full, valence band is full of electrons. So hence there are a lot of electrons available, and there's a huge potential applied already. So hence suddenly there's a huge amount of huge flux of electrons tunneling from this side to this side, and this results in a very high negative current. Another is avalanche breakdown. In avalanche breakdown, what happens is the electric field across the junction, it becomes very high, and this electric field causes the this causes electron hole pair generation in the junction. Electron hole pair generation over the junction, and this results in a generation of electrons in the excess electrons in the n side and holes in the p side, and this causes, and since there's already a huge potential applied, huge reverse bias potential applied, this causes the very high number of electron hole pair generation and very high number of carriers going towards the junction, and going towards the electrodes, and hence the current in this case also increases abruptly. So we will take a 5 minute 2 minutes break. I will come back in 2 minutes. So next topic is non-ideal diode. So so when we were deriving the ideal diode equation, we had made assumptions about low level injection and the current in the constant current in the depletion region. But in real life cases, the a diode is not ideal, does not give ideal condition regions. So we had studied in the reverse bias. So, so the ideal case would be at constant current, but what happens is in there is generation of electron hole pair. So in non-equilibrium condition, there will be generation of electron hole pairs to restore the equilibrium in the depletion region. So for reverse bias condition, the generation of electron hole as the as you go more and more reverse, the depletion width is increasing, and due to that, the number of electron hole pairs generation will also increase. So that so instead of a constant value, you will have some increase in the current till the breakdown, and at breakdown you will have a abruptly high current. For forward bias, what will happen is for very small very small forward bias voltage, the excess the excess electrons and holes will recombine till so this is only for when VA is few kts, so like few multiples of 26 millivolt for room temperature 300 Kelvin. After that, your diffusion current becomes dominant and your diode starts showing ideal diode conditions up to certain point. What happens is at after certain point you reach the limit of low level injection, so the injection your minority carrier injection becomes higher than your majority carriers, and you go into high level injection regime. And in high level injection regime, your diode equation becomes J equals to Js exponential q Va by 2 kt minus 1. So your slope becomes half. So your slope is now half than earlier. So in the ideal case, it's q Va by kt, and for high level injection regime, it's q Va by 2 kt. And if you go even further, there will be further reduction in current, which will happen due to series resistance. So due to, so at this high level of current, so your quasi neutral regions, which is your p type and n type regions, they are assumed to have low resistivity because they are doped. So we assume there low resistivity. So for low current density, the resistance drop across these junctions, but they will have certain resistance associated with them. So for small currents, the higher voltage drop across these resistance across these junction across these quasi neutral regions are considered negligible, but when you have very high amount of current, the the voltage drop, which is V equals to IR, across these quasi neutral regions becomes very high. Hence the actual actual voltage reaching the depletion region, your junction region, is much lower than the applied value at the ends of the diode. So due to the actual applied value at the junction being lower, your current also decreases, and hence you see a further dip in your current. So so you can so for non-ideal case, you have five regimes. So one is first regime is your junction breakdown regime. Second is your thermal generation in the depletion region. So as depletion region is increasing, your number of electron hole pairs generated across the depletion region is also increasing, and that is giving a rise in the current. Third is recombination in the depletion region. So for low applied voltage when low applied voltage when the diffusion current is not dominating, the recombination inside recombination of excess carriers inside the depletion region will reduce the carriers available for diffusion, and hence you will have a high difference in current. Then you have your ideal region, and after that you have a high level injection regime where our slope is q by 2 kt. In your ideal region, the slope is q by kt. And fifth, then your last is your series resistance regime. So this is still your so if series resistance was not there, your high level injection regime will continue. But due to series resistance, there's a voltage drop at the quasi neutral regions, which is causing a further dip in the slope. Now, how will temperature affect your current? As the temperature increases, carriers have more energy to cross potential barriers. So, as temperature increase, your number of carriers will increase. Hence, your saturation current will also increase. So, so in reverse bias, your uh, first first thing you will notice is that your reverse saturation current increases. Another thing, what will happen is your threshold voltage will reduce, as threshold voltage is inversely proportional to your Ni square. So since temperature increases, your Ni will increase, so your threshold voltage will decrease. So you will and your slope is q by kt. So as t increases, your slope also changes. So your net positive will change like this. So earlier it was like this, now it will look like this due to threshold shift. Also, what will happen is your breakdown voltage will also increase. So as your temperature increases, the scattering between carriers will also increase. So your scattering time will reduce, and due to this, your carriers will not be able to gain very high kinetic energy. So they will need a much larger voltage for breakdown to happen. So now a recap of what we studied today. So this week was devoted to modeling the steady state response of a PN junction diode. So we had a qualitative description of diode operation using band diagram and various parameters to characterize the forward and reverse bias for ideal diode. As and we also studied non-idealities and different processes and their impact on diode parameters. Then we studied the temperature dependence and its impact on threshold voltage, reverse saturation current, and reverse breakdown voltage. So in forward bias PN junction, your band diagram will look like this. As we had studied, your potential barrier will reduce. The minority carriers at the edges of the depletion region uh, is given by NP minus XP and equals to NP naught exponential QVA by KT. Pn of Xn equals to Pn naught exponential QVA by KT. So law of junction is the NP product. So this equation is valid all across the junction. So NP equals to Ns square exponential QVA by KT. The the variation of magnetic carrier concentration from edges is given by the equation delta Pn of x equals to Pn of x minus Pn naught, which is Pn naught exponential EVA by KT minus 1 exponential minus x by xn by Lp. And similarly, delta Np of x equals to Np of x minus Np naught, which is Np naught exponential EVA by KT minus 1 exponential x by xp by x by ln. So the total current is given as the summation of peak hole and electron current, so which is E dn delta d of delta n by dx minus E dp d of delta p by dx, which becomes J total E dp by Lp Pn naught plus E dn by ln np naught exponential E Va by kt minus 1, and this then is called reverse saturation current Js. For a reverse bias case, your depletion width will increase, your potential barrier will also increase and becomes EVBI plus VR. Your width of the depletion region is given as W equals to square root of 2 epsilon SI by Q 1 by NA plus 1 by ND VR plus VBI. And the maximum electric field for reverse bias is given as E max equals to minus 2 VBI plus VR by W, which is the same as what we had studied last week. Since we have a separation of positive and negative charges in the depletion region due to reverse bias, there's a capacitance associated with the PN junction. If we consider an abrupt PN junction as biased in reverse bias voltage VR, then the depletion width across the junction increases and forms a capacitance known as depletion or junction capacitance. C depletion equals to Cj, and its value is typically in picofarad per centimeter square to nanofarad per centimeter square. So you can calculate Cj equals to epsilon Si by W, which is square root of Q epsilon Si Na Nd by 2 Na plus Nd Vr plus Vbi. So hence for abrupt junction, the capacitance varies inversely with square root of total voltage drop across the junction, which is Cj is proportional to square root of 1 by Vr plus Vbi. And if you take a linearly graded junction, the capacitance will vary with the cube root, because we had studied that W is the depletion width for a linearly graded junction is given as the cube root of VBR plus VBI. Hence, the capacitance will vary as cube root of 1 upon VR plus VBI. So if you plot for an abrupt junction, if you plot 1 by C square versus VR, you will get a slope which will be 2 upon E epsilon ND. So this ND is for an for a one-sided junction where N is greater than ND. And if you extrapolate it, you can calculate your VBI. And your we know that your reverse saturation current is dependent on temperature. So we can say that the reverse saturation current almost doubles for every 10 degrees Celsius rise in temperature. So that is JS2 is approximately JS1 into 2 to the power delta T by 10, so where delta T would be in Celsius or Kelvin, because 10 degree Celsius change is equal to 10 degree Kelvin change. Sorry, 10 Kelvin change. So now we come to practice questions. So first question is, the capacitance of a PN junction diode decreases with the increase in the forward bias voltage, increases exponentially with the increase in the forward bias voltage, increases linearly with the increase in forward bias voltage, does not change with the increase in forward bias voltage. The right answer would be increases exponentially with the increase in forward bias voltage. So as forward bias voltage increases, your diffusion capacitance increases exponentially, because injected carriers will increase exponentially. So your charge will increase exponentially. The built-in potential of an abrupt PN junction is 0.75 volts. If the junction capacitance Cj at a reverse bias VR of 1.25 volts is 5 picofarad, what is the value of Cj in picofarad when VR is 7.25 volts? 1.5 picofarad, 2 picofarad, 4.2 picofarad, 4.5 picofarad. So for this, you have to use the junction capacitance formula, that is 1 by C is proportional to square root of VBI plus VR. So the answer to this will be 2.5 picofarad. So you have to use the formula Cj is proportional to 1 by square root of Vbi plus Vr. So Cj2 by Cj1 will be square root of Vbi plus Vr1 upon Vbi plus Vr2. So this will be 2 volts. This will be 8 volts. So this will, if you saw, this will be 1 by 4. Square root will be 1 by 2. So it will be Cj 1 by 2, which is 5 by 2 is equal to 2.5. A silicon bar is doped with donor impurities Nd equals to 2.25 into 10 per 15 atoms per centimeter cube. Given the intrinsic carrier concentration of silicon at T equals to 300 K is Ni equals to 1.1 10 per 10 per centimeter cube. Assuming complete impurity ionization, the equilibrium electron and hole concentrations are: take Kt by Q equals to 25 milli electron volts and Ln2 equals to 0.693. N naught equals to 1.5 into 10 per 16 per centimeter cube and P naught equals to 1.5 into 10 per 5 per centimeter cube. N naught is 1.5 into 10 per 10 per centimeter cube. P naught is 1.5 into 10 per 15 per centimeter cube. N naught is 2.25 into 10 per 15 per centimeter cube. P naught is 1 into 10 per 10 per centimeter cube. And N naught is 2.25 into 10 per 15 per centimeter cube. And P naught is 1.5 into 10 per 10 per centimeter cube. I think there is some typo in the question. So P naught should be 1 into 10 per 5 per centimeter cube. But I think there's some typo in the question. So N naught will be 2.25 into 10 per 15 per centimeter cube, which is equal to Nd. So N naught will be equal to Nd and P naught will be equal to Ni square by N naught, which is Ni square by Nd. So which will come out to be 1 into 10 per 5 per centimeter cube. So this should be 10 per 5, not 10 per 10. For questions 4 and 5, if a PN junction is forward biased, then for minority carrier distribution, answer the following question based on the graph given below. So you have given this graph for the minority carrier dynamics. Determine which side of the junction is more heavily doped. P side is more heavily doped. N side is more heavily doped. Both sides are equally doped. Both sides are lightly doped. That is correct. The P side is more heavily doped because the depletion width is smaller on the P side. Hence, it has a higher doping. Which region exhibits a larger diffusion length for minority carriers? P region, N region. Both regions have the same diffusion length. Neither region exhibits diffusion of minority carriers. So that would be N region. So if you see, if I want to get to half of the initial concentration value, I will reach it quicker compared to here. So in the N region, the my diffusion length. So in the N region, the gradient is low. The gradient is lower, and hence the diffusion length is larger in the N region. For every 10 degrees increase in temperature, the reverse saturation current of a PN junction will increase by, it remains the same, 10 times, 2 times, 4 times. So the diffusion length does not depend on the doping. Diffusion length is Ln, which is given by your which is given by your Ln is given as square root of dp tau p. Sorry, Ln is given as square root of dn tau n, and Lp will be square root of dp tau p. So it depends on your diffusion constant and your recombination time. It does not depend on doping. So from this graph, so for to get diffusion length, you have to look at the carrier dynamics. Here the here the carriers are depleting faster. Here they are depleting slower, which means the value for L. So which means LP is higher than LL. So here they are moving with respect to LN, and here they're moving respect to LP. So you see LP is higher, and LP is active in the N region. So N region is exhibiting higher diffusion length for minority carriers. So reverse saturation current remains same for every 10 degrees increase. It becomes 10 times, 2 times, or 4 times. That is correct. It becomes 2 times. So it is proportional to t square exponential minus Eg by kT. So for every 10 degree rise in temperature, the current will Js will increase by 2 times. Consider the following parameters in a silicon PN junction. Nd equals to Na equals to 10 per 16 per centimeter cube. Ni equals to 1.5 into 10 per 10 per centimeter cube. Dp is 25 centimeter square per second. Dn is 10 centimeter square per second. Tau p equals to tau n equals to 5 into 10 to the minus 7 seconds. And epsilon r equals to 11.7. Determine the ideal reverse saturation current density at t equals to 300K. 4.16 into 10 to the minus 8 ampere per centimeter square. 4.16 into 10 to the minus 9 ampere per centimeter square. 4.16 into 10 to the minus 10 amperes per centimeter square. 4.16 into 10 to the minus 11 amperes per centimeter square. So formula for ideal reverse saturation current density we have just studied which was around the value J. We had studied the in in lecture. We have just studied the formula for JS. We have to use that. So this will be equals to 4.16 into 10 raised to minus 11 ampere per centimeter square. So formula you have to use is Q dn by ln ni square by na plus dp by lp ni square by nd, where ln is square root of dn tau n and lp square root of dp tau p. So ni square by na will be 2.25 into 10 per 20 by 10 per 16, which is 2.25 into 10 per 4. Similarly, this will be also 2.25 into 10 per 4. And you have to calculate ln lp, put it here, dn from the value, all the values you are given in the question. You just have to put it here. What is the main difference between Zener and avalanche breakdown in terms of carrier generation? Zener involves minority carriers, avalanche involves majority carriers. Zener involves tunneling, avalanche involves impact ionization. Zener occurs at high voltage, avalanche occurs at low voltage. Zener creates fewer carriers, avalanche creates more carriers. So only B is correct. So both Zener and avalanche both occur at high voltage. For a break, your breakdown voltages are very high values. So the correct answer is B. Zener involves tunneling and avalanche involves impact ionization, where the kinetic energy is so high. Kinetic energy of carriers is so high that they are able to they are they're kinet so high that they are able to ionize the ionize atoms and create electron hole pairs. If the depletion region width of a PN junction increases from 150 nanometer to 300 nanometer due to an increase in reverse bias voltage, by what factor does the junction capacitance change? 0.25, 0.5, 2, 4. So correct answer will be 0.5. So we know junction capacitance is inversely proportional to depletion width. So if depletion width becomes double, junction capacitance will become half. In the reverse bias, a change in temperature results in in a reverse bias. A change in temperature results in a shift in the reverse saturation current Js. Choose the correct temperature relation along with the reason. Tc greater than Td as Js is proportional to 1 by Ni square. Tc less than Td as Js is proportional to 1 by Ni square. Td greater than Tc as Js is proportional to Ni. Td less than Tc at Js is proportional to Ni. Tc less than Td as Js is proportional to Ni square. Tc greater than Td as Js is proportional to square root of Ni. So the correct relation is E Td less than Td and Js is proportional to Ni square. So this we know Js is proportional to Ni square and Td is always greater than Tc. So this is all I had for today. If you have doubts, you can ask, or if you are done, you can leave the So, so this is straightforward. So you have to calculate the minority carrier junction concentration at the edge of the region for forward bias of 0.6 volts. So, so the formula for that we had studied is Pn at x of n, which is so this is these are the edges of the space charge region or depletion region. So so first you calculate Pn naught, which is Ni square by Nd, which comes out to be 10 power 4. If you take Ni as 1 into 10 power 10 per centimeter cube, and this is Ni square upon 6 into 10 power 15. So this will be 10 power 20 upon 6 into 10 power 15. So that will be 10 by 6. So 10 by 6 has been approximated to 2. 2 into 10 power 4. And then, so the value you know is Pn naught exponential Q Va by Kt. Va is given as 0.6 and K, so Kt by Q for 300 Kelvin we know as 26 millivolts. So it becomes 0.6 upon 0.026. So if you calculate that, point point 0.6 divided by 0.026, you get around, you get approximately e power 23. So if you take the exponential of this, and then you multiply it with 10 power 4, you get approximately 1 into 10 power 14. So the 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 carrier concentration of holes at the edge of the n region is 10 power 14. Similarly, if you calculate for this side, you will get 2. So here your Pn naught was 10 power 4. Here Np naught is around 2 into 10 power 4. So this exponential QBA by KT is same for both the cases. So here it just instead of Pn naught you will put Np naught. So you will get, so if here you are getting 10 power 14, here you will get 2 into 10 power 14. So the electron concentration at the edge in the P region is 2 into 10 power 14. You see both 10 power 14 and 2 into 10 power 14 are less than the doping values, which is 10 power 16 and 6 into 10 power 15. They are one and two order less. So we still call them low level injection because they are less than the majority carrier value.